So I pulled my calculator up and I wanted to just go back to question 4 and 5 on page 1 of your notes sheet. And to get those values, again, remember we go to second distribution. This is what you learned in chapter 6. And so all of those skills are going to still be coming in handy. We go to normal CDF, enter, and then lower bound 46, enter, upper bound 54, enter, mu is 50, and sigma is 4. And this is going to look a little different on some people's calculators. On my other calculator, I just type it in, normal CDF comes up, and then I put in the 4 values separated by the comma button, and then close parentheses, enter, and that's how we got the 0.68 for question 4. And then for question 5, notice that it's exactly the same except for the very end. So one trick I like is to do second entry, and it pulls up what we already just did, and then I can just arrow back, delete, and then say 4 divided by second square root 10, close parentheses twice. I don't like that. Delete, and then I think I have to arrow out to get myself out of that square root. Oh, I don't even need parentheses. This calculator is a little slicker than the one I normally work with. Enter, and there's your 99.84%. So that was for questions 4 and 5. And then 7 and 8 are similar. Again, it's almost exactly the same question, but 7 is about x and 8 is about x bar. And again, because we're applying the central limit theorem, x is normally distributed and x bar is normally distributed, but x bar has a different sample standard deviation. And when we're trying to do the probability that x is greater than 52, we are going to kind of want to draw a picture of this. Here is our distribution of the sample means. Sorry, here's our distribution of the student heights. And that was x is distributed normally with a mean of 50 and a standard deviation of 4. Let's try to squeeze that in here. It won't let me. And then if I want to talk about x bar is going to be a much narrower distribution. Okay, just went off the charts there. X bar is distributed normally. Let me back up here. X bar is distributed normally with a mean of 50 and 4 divided by root 10. And so you can see that when I say what is the probability that x is bigger than 52, let's just say 52 is right here. So what is the probability that x is bigger than 52? There's actually quite a bit of area to the right of this line under the red distribution. So that's like 30%. Okay, 31%. And then when I go look at the green distribution and I say what's the likelihood that x bar will be bigger than 50, now I'll do this in green. That shaded area is just going to be a lot smaller. So it comes out to be 0.06. Chances are that the sample mean is going to be pretty close to 50. And so getting a sample mean higher than 52 just seems pretty unlikely, 6% chance. And again, the way we do these is second distribution, normal CDF, and this time we're starting at 52, that's our lower bound. Upper bound is 1, second E, 99, enter, mu is 50, sigma is 4, paste, and that's where we get our 31%. And then I can just go to second entry, go back and change this to 4 divided by second square root 10, arrow out of the square root, close parentheses, enter, and that's how I got 6%. And you can see that we could be more accurate if needed. We could say 0.0569 0.3085, but that would be 30.85% or 30.9%, depending on how much accuracy your online homework is asking you for. Interpreting these results, 31% of children are taller than 52 inches. That's what we were talking about here. And only 6% of the sample means will be higher than 52 inches. There is less variability in the sample means than there is in the original data set. Once you get this, you'll be like, duh, that's obvious. But of course, it's a very formal mathematical principle as well. Find the 90th percentile for a child's height. Then write a sentence explaining your answer. I kind of want to draw a little sketch for this one too. Pictures are always how I think about things. So the 90th percentile is right here. It's unknown, so we're like not sure where that value is, but I do know that the area to the left of this is 0.90. So 90% of children are shorter than X. And if I want to find out what X is, I use the inverse normal, and I put in 0.90, which is the area to the left, and then I give it mu and sigma. So this is what we learned last unit. Second distribution, there it is, inverse normal, enter, area 0.90, and this has the options of left, center, and right, but I'll leave it on left. Mu is 50, sigma is 4, and then I can just arrow down and have it calculate what the X value would be. And it's saying 55.13 inches. So 55.13 inches is the X value that we were looking for. Find the 90th percentile for the sample mean. Write a sentence explaining your answer. So repeat that process, but with 4 divided by square root of 10, and we get a lower number. So now we're talking about this skinny distribution of the sample means. Oh, I wanted that to be green. So the distribution of the sample means is this really skinny distribution with less variability, and I'm trying to find a value X that has 90% of the data to the left of it. So again, what is my X? And it turns out that X is 51.62 inches. So you have to be taller to be the 90th percentile of the kids, and you don't have to be as tall to be the 90th percentile for the sample means. And I just realized that I should have put X bar on that guy, because that's a distribution of X bar that we're talking about. Second distribution, inverse normal. So the only thing I change here is I go in and I say 4 divided by second root 10. Oh, there's the parenthesis. Okay, enter. And arrow down, enter, enter. 51.62 is what I'm getting. Okay, so 4 more questions. What if we change the sample size to n equals 30? We're still operating under the same original distribution of child heights. Can we restate the distribution of X bar? Sure, X bar is now normally distributed with a mean of 50, 4 divided by the square root of 30. So what is going to change about the shape of the distribution? It's going to be narrower, because 4 divided by root 30 gives us a smaller standard deviation. And the smaller the standard deviation, the narrower this distribution will be. So now I can re-ask you all these questions about x bar, and the answers are going to change a little bit. The probability that x bar is between 46 and 54 is now almost 100%, very, very close. And the probability that x bar is greater than 52 just got a whole lot smaller. Before it was 0.06, and now it's less than 1%. And then this last question just emphasizes what I just said. When n equals 10, the standard deviation was 1.26. When n equals 30, it was 0.73. The amount of variation in the sample means decreased when the sample size increased. I hope that makes sense to you intuitively.